Our first case study is going to be presented by Jen Simoni. She is going to talk about the Family Forest Carbon Program. And through the American Forest Foundation's Family Forest Carbon Program, Jen Simoni helps woodland owners access carbon markets in order to fight climate change while earning income from their land. She previously worked as a project manager for the My Wisconsin Woods Initiative and as a forester for the Wisconsin Department of Natural Resources. She holds a bachelor's degree in forestry from UW-Madison and a master's degree in natural resource management from UW-Stevens Point. I'll turn it over to you, Jen.
Great, thanks, Deb. And thanks for having me today. Let me just go ahead and get myself set up. There we go.
While you're getting set up, I'm just going to remind people that the Padlet is still open. So if you have any comments that you want to make, you thought about something over lunch or something just popped in your head, you can certainly still access that and add that information.
Okay, hopefully you're seeing some slides then.
Yep.
Great. Okay, well, again, thank you, Deb, and thank you for inviting me here today to share a quick overview of the Family Forest Carbon Program. Hopefully you're able to grab some lunch and get back and get comfy. As Deb mentioned, I'm Jen Simoni. I'm the Midwest Director for the Family Forest Carbon Program and work for the American Forest Foundation, and I'm based out of Verona, Wisconsin. So as the climate crisis intensifies and we race to drastically reduce our emissions by 2030 and reach kind of net zero emissions by 2050, states, businesses, and the global conservation community are increasingly realizing the potential of natural climate solutions as one way to mitigate the impact of climate change. A recent study by the Nature Conservancy indicates that natural climate solutions like reforestation, natural forest management, and avoiding land conversion holds the potential for 37% of the needed mitigation globally through 2030, yet currently only receives 0.8% of climate financing. And according to subsequent research, one of the greatest opportunities to implement these natural climate solutions in the US lies within our nation's working forests, where improved practices could lead to hundreds of millions of additional tons of carbon being sequestered. Yet, the current carbon markets that encourage these improved practices really exclude the largest portion of our nation's forests, the 290 million acres or 39% of the forests owned by families or individuals who own on average between 60 and 70 acres in size. For these landowners, the transaction costs to develop traditional carbon projects are just simply too high and the commitments are just too long. And so as a result, more than 98% of the forest carbon projects in the US have been developed on properties exceeding 5,000 acres in size, leaving less than 1% of the carbon projects being developed on ownerships between 20 and 1,000 acres. And so really here lies both the opportunity and the challenge before us. And in 2017, the American Forest Foundation and the Nature Conservancy partnered to build a new and innovative program called the Family Forest Carbon Program. And FFCP enables family forest owners like Susan here to address climate change, improve forest health, and earn income from their land through these emerging voluntary carbon markets. The goals for our program are ambitious, and as two not-for-profit organizations, our missions are to drive real conservation impact and not profits. And so therefore, to reach real climate impact, we are striving to engage 20% of family-owned forests acres nationally by 2030 in order to sequester and store at least 50 million tons of additional CO2 equivalents annually. And because of its practice-based approach, we're also encouraging all those additional benefits that come with good forest management, like improving wildlife habitat, increasing quality forest products, overall forest health, water quality, and of course, recreational opportunities. What makes FFCP a unique carbon program is its practice-based approach, where landowners are getting paid to follow specific forest management practices, which have been scientifically demonstrated to enhance carbon storage over business as usual. Now, this differs from traditional carbon projects that base their payments on carbon inventories or stocks that accrue over the life of the contract or the project. And so looking at this graphic, you can see that we have two stands that both start with the same forest carbon conditions. And on the top line, we have the properties enrolled in the program, and the bottom line is our baseline, or properties that are not enrolled in the program, but are being monitored through forest inventory analysis data that is obtained and maintained by the Forest Service. And so let me say that we're not implying that all timber harvesting out there is being done bad or unsustainably, but to demonstrate kind of what can happen in woodlands that are being high graded or having more frequent harvests or at higher intensities. And you can see how that can change the carbon stocks over time. So when we compare our enrolled properties, that top line, who are conducting kind of less frequent or less intense harvesting, to properties outside of the program, sort of that bottom line, we can calculate the difference in the carbon and any additional carbon, sort of that light shaded green, that we observed on our enrolled properties is what we can then turn into a carbon credit and sell. So this new method of calculating the carbon sequestered and stored by the program, we believe provides a more accurate climate benefit. Modeled after medical trials that measure a drug's performance compared to a control group, this method really allows us to isolate the family forest carbon program as the single variable that contributed to the carbon generated, and removes the challenges and the criticisms around projected or modeled baselines that are often used in traditional carbon programs. So here's kind of a graphical description of what that methodology looks like. And so at the time of enrollment, a project is randomly selected to be monitored for the contract period, which is depicted by the two red pins within the shaded parcel in the center there. Now those monitoring plots are then matched with 10 highly similar but unenrolled properties, which again are being monitored through FIA data, which are the pins with the plus signs. And those 10 plots make up what we call our composite control or our dynamic baseline. And so we then annually monitor and calculate the difference in the carbon stored between the enrolled property and that composite control over the next 20 years, and then can monetize and sell any of the additional carbon that we observe. And it's really this use of the dynamic baseline that provides an extremely credible claim of additionality, which then results in high integrity carbon credits that will be verified and sold under Verra's verified carbon standard. And verification under these international standards is really critical to being a credible program and ensuring that the program is producing a true climate benefit. This methodology, or the way of this carbon accounting, was approved by Verra in October of 2022 and is now publicly available for others to view and use as well. As a program, we are committed to continual improvement and refinement, both to our program and the way that we account for carbon, to ensure that we are incorporating the latest science, technology, and innovations. It's also important to mention that the integrity of our program and our organizations rests on the integrity of the companies to whom we sell our verified carbon credits to. And so companies go through a rigorous independent assessment by both AFF and TNC and must demonstrate that they are taking a comprehensive approach to reaching their climate goals. One, by first reducing and avoiding emissions before working to neutralize those they cannot eliminate through the purchase of carbon credits. Not only are we proud of our approach and the integrity we bring with this new carbon accounting methodology, but we believe we offer value to landowners beyond carbon. And so again, remember, we're not paying landowners for the carbon on their property, but to follow good management practices to keep their woods healthy and productive. And so therefore, we provide annual payments starting 60 days after enrollment and every year for the next 20 years to help support whatever it is they're looking to do, invasives control or setting up a timber sale, or simply helping to pay for the taxes or the maintenance costs. Through this enrollment process, we're also connecting landowners with foresters and professionals to support project planning, as well as developing or updating management plans at no cost to the landowner. So this is really helping landowners give them a roadmap to help achieve kind of all of their woodland goals into the future. And again, because the program is practice-based, we offer practices that not only help keep more carbon on the land, but provide other benefits like timber production and enhancing wildlife habitat. We're currently offering enrollment in several states in the Central Appalachians region, as well as the Northeast regions, and we just opened enrollment in select counties in Wisconsin, Minnesota, and Michigan, and are planning to expand to the South next year. To be eligible, landowners must own at least 30 contiguous acres in an active service area. While land can be enrolled in conservation easements or other state or federal programs, as long as they don't impose any legal restrictions on timber harvest activity, the land cannot be enrolled in another forest carbon program. Of course, our program's mission, values, and the impact that we're seeking also has to match the landowner's vision and goals for their land and their legacy as well. And then in addition to kind of this general program eligibility, there are additional eligibility criteria that's tied to the specific forest management practices that might be available within a region. So one example of a practice that we offer in the Central Apps as well as the Midwest is called growing mature forests. And this practice is intended to allow a forest to grow older and larger trees than the average forests in the landscape. And so this practice really promotes long-term forest health, improves habitat for the numerous wildlife species that rely on mature forests, and increases the commercial and environmental value of the woodland, while still allowing landowners to maintain a working forest. In the Midwest, landowners receive $10 annually for every acre that they enroll in this practice for the next 20 years, or $200 per acre over the life of the contract. And these payments rates are going to vary by practice and by region, kind of based on their anticipated carbon benefits and their associated kind of harvesting guidelines. By enrolling, in growing mature forests or any of other practices that we offer, the landowner is really committing to abiding by the contract terms for a 20-year period. That includes following the harvesting guidelines that's laid out for that practice, which will vary, and harvesting is optional. It's not required. They must have an updated management plan. And again, they can't enroll in any other carbon program or another program that would restrict harvesting or limit their timber rates. By doing that, they have to report out to us every 5 years to let us know if there's been any natural disasters, any storm damage. If they choose to do a harvest, we need to take pre and post harvest data. And of course, if there's any ownership changes. Enrollment is fairly easy, and if you work with landowners interested in learning more, can get started at familyforestcarbon.org. Landowners will be able to find their property with an interactive parcel map where they can choose the parcels that they're interested in learning more about their eligibility. Through that system, that interactive map, as well as a few questions that'll let a landowner know whether they're eligible and which practices they might be eligible for. If they continue with that process, we'll set up a time to speak with them, answer their questions, further understand their interests and eligibility. If we proceed, they'll be connected with a forester to either do a property site visit to do some of that project planning or to review their management plan. And if they choose to move forward after they've seen sort of the financials and the contract estimate, we move to that contract process and get that all squared away. As I mentioned, payments start 60 days after that contract is signed, and they'll receive that annually for the next 20 years. Throughout that time, we'll be working with them to make sure that we support them through their stewardship journey, connect them to foresters when they need assistance with any projects, as well as implementing the practices. Since 2020, we've launched in 9 states and enrolled over 35,000 acres, enough to generate almost 1 million verified carbon credits over the next 20 years. And we've committed to paying over 200 landowners over $8 million in the next 20 years. And we are just getting started. I know there's not enough time for questions, but you'll receive these slides with my contact information, and I would love to continue the conversation.
Thanks, Jen. Appreciate that. Interesting information. Now we're going to move on to our next case study, which comes from the Indigo Ag Agricultural Carbon Management Group. And our presenter is Pive. I'm going to do this. Sundareshwar, and he's the Director of Sustainability Standards and Compliance at Indigo. He has almost 30 years of experience in environmental and climate issues in academia, the federal government, and consulting for the private sector. He has guided the development of environmental policies internationally, has contributed to national dialogue on carbon sequestration, and understands how sustainability information can impact enterprise value for businesses. He is adept at identifying a suite of material, environmental, social, and governance issues across diverse sectors, developing standards and metrics, designing projects to promote triple bottom line, which means planet, people, and profits, and auditing compliance to regulatory requirements. He has deployed his scientific expertise and technology innovation in ESG issues for sustainable international development and to improve R&D operations in a large organization. He has a PhD in biology from the University of South Carolina and an MS in life sciences from the University of Bombay, India. I will turn it over to you, PV. You might be on mute. We can't hear you.
Is it better now?
Yes, now we can hear you.
Great. I was saying thank you, Deb, for that wonderful introduction and pronouncing my name right. I think as a former professor, I said, yeah, if you were in my class, you got an automatic A. So thanks again for this opportunity and your interest in Indigo's operations. And I'd like to share with you very briefly an overview of what Indigo is doing in the agricultural carbon management space. So Indigo was actually founded in 2013, and we're basically an ag-tech company with a mission to harness nature to help farmers sustainably feed our planet. And what we do is we have two major, we operate platforms, basically a digital products platform and a biological products platform. And today I'm going to be focusing on the Carbon by Indigo, which is a part of our digital products platform, where we actually generate carbon credits from the agriculture sector. So, and we do that by actually leveraging 5 practices that have been proven to increase soil carbon, whether it's planting cover crops or adopting no-till farming, or crop rotation, reducing agricultural inputs, or incorporating livestock. And we know there are so many additional benefits of actually improving soil carbon, which is improved drought tolerance, we have better flood resistance, we get enhanced yields, and of course, the nutrient retention in the system goes up, so you need to put in less inputs, for example. But the added value here, as we say, is our ultimate stakeholder is the atmosphere. And one of the ways we really want to make that impact is to ensure that we can capture the soil that is actually stored or sequestered, the carbon that is sequestered in the soil, and transact that into as a commodity in the voluntary carbon market. And there are 2 carbon markets. One is the compliance market and the other voluntary carbon market. And Tim earlier this afternoon provided an introduction of the voluntary carbon market. And thanks for the kind words, Tim, about Indigo. We really pride ourselves about, as being using science and technology to help generate really high integrity carbon credits. And so as you can see, the voluntary carbon market is really, really taking off. And in 2021, it touched almost $2 billion. In 2022, again, it has crossed the $2 billion in the annual volume of sales. And on the right-hand side of the chart scale, you can see the cumulative value, which far exceeds $8 billion now. And this is another slide that was that Tim had actually shared earlier. So this is an overview of how a voluntary carbon project system ecosystem works. So in this case, you have growers who grow and harvest and adopt some land management practices. We have project developers and aggregators who quantify and report this, and the report is submitted to the validation and verification bodies, which verify the performance that's happened on those lands. And eventually, the offset projects through registries actually approve and issue the credits, which are eventually sold to the voluntary buyers, which they can use to offset their greenhouse gas footprint. And here throughout this process, I think the robustness of the process stems from the oversight that's provided by the registries, which actually dictate the validation and verification processes that are adopted by independent third parties. And they also provide the oversight on the projects that are developed. And the payment that comes from the buyer actually goes to the project developers, and for example, Indigo in this case, and then we distribute it to the growers. See, the advantage of doing that, as Tim was saying, if you want to participate in this market, there are a lot of costs associated with, participating in a voluntary carbon market, especially that stems from quantification, verification, and transacting these different processes. And that's why the project developers and aggregators really help by allowing a lot of people to actually participate in this process much more effectively. So a bit more nuanced, granular information on how Indigo does it. We enroll growers in our carbon offset program, and Indigo then uses to help establish a baseline for these growers. And we support farmers in transitioning and making into carbon storing farming practices, which then we collect data from the farmers on land use change and the management practices that they are deploying, which is used into our system, which we call the Indigo pipeline, which basically processes this data to quantify greenhouse gas abatement and soil carbon sequestration. This is eventually verified, and the verified credits are sold for offset, and the revenue is distributed among the various stakeholders, and the value is transferred to the grower. We are able to do this in a very effective and efficient manner because we built an easy-to-use software for the growers to actually sign up. They can enroll using this, they can map their fields and farms, provide management data, and also receive payments for program outcomes. So throughout this whole process, as I've said, we rely heavily on science and technology that builds the quality of the credit that we generate, and it allows us to actually operate at scale. And that's a pretty big deal. So we have so far enrolled millions of acres. We operate in about 32 states with expanding to EU and Latin America, work with 15 eligible crops. And in the reporting period one, we generated about 22,000 tons of credit, 22,225 credits. And we're paying out about $30 a credit to the farmers. So collectively with the reporting period one and reporting period two, we've had about $4.7 million in payments to farmers yet. And we are supported by a lot of leading companies in basically using the agricultural space to come up with climate solutions, right? And this network is growing, where these companies actually buy credits from us, and that way are actively participating in our program. So where do we go from here? As I said, the second verification is almost done. We should be, announcing the issuance of the credit in the next, very soon. And then, of course, there's going to be the third and the fourth verification that allows for us to continually add value to the farmer's operation. As we said, we're expanding globally. We have projects in Europe that's based on BERA methodology. And we continue to build research collaboration and expand our project domain and to see where are different approaches by which we can add additional value to farmers. And an example of that is we partnered with the American Farmland Trust under the Climate Smart Commodities grant to support sustainable beef production. And if you caught the first slide about Indigo, where I talked about the two platforms, the digital platform had something called Market Plus. And the Market Plus is about expanded supply chain solutions where we are providing sustainable produce from agricultural sector to our farmers. That's all I have. I wanted to leave some time for some question and answers. But if you have any questions, please reach out to me and you will have my email address. I'll do my best to answer those questions now or later. If I don't have the answer, I'll put you to the right, point you to the right person. Thank you for the opportunity again. And I really enjoyed hearing comments this afternoon. So thank you.
Evie, and do we have any questions or comments? We have a couple minutes. Okay, we have one question in the chat. Are the two crops you mentioned corn and soybeans?
So we have 15 different crops that are eligible. Yes, corn and soybean are definitely part of that mix. Okay. So we also have wheat.
Any other questions?
PV, this is Tim Bay. What's the typical length of the contract that you're signing up? And then are there clawback terms should there be a problem in the production of the carbon credits?
Yeah, excellent question. I think the length of the contract is 30 years. And, with regard to clawback, yes. So if I may go back to sharing my screen. Please bear with me. So here, one of the things, I presume this is what you're referring to. So for RP1, we issued 22,000 credits. Out of that, about 19,000 credits were sold, were available for purchase. And the rest were put in a buffer pool to address any reversals. And I presume that's what you're saying. So we're creating a project-based buffer pool to address avoidable reversals.
Yes, that's exactly what I was referring to. Thank you. Because
so we don't. One important thing is that the farmer, so we absorb that reversal, right? So by creating a buffer pool, so it doesn't actually percolate down to the farmer.
There's time for one real quick question then?
Yeah, real quick one, go ahead.
So I've had numerous conversations with people in your shop and all sorts of climate finance folks about the merits of continuing to utilize the proprietary.
That's an excellent question, Tim. And I think this is something that you touched on in your presentation too. The challenge is that in the voluntary carbon market space, when we have these registries, we have established methodologies that everybody abides by, right? Ultimately, it goes to the integrity of the credits that are being generated. And as long as we can ensure that the credits that are generated under either a government program or under these voluntary markets using proprietary methods, they're of high quality, high value, then that's okay, I think. But the challenge is that sometimes right now, with the new approaches, we do not have any system in the government space to allow for this kind of quantification and addressing the baseline issues and quantifying carbon with such a rigor right now. We can estimate carbon, right? But quantifying carbon is based on business as usual, for example. So ensuring how those things are actually being tracked and monitored and accounted for is very important. So yeah, if there is a very robust approach, yeah, that should be okay. And creating a general table might be challenging because it is so highly variable, which is dependent upon the management practice. And of course, depending upon the time. So it's not about how much carbon you have at a particular time point. It's how it is in relation to what the business as usual is. I hope that answers things.
Thank you.
Okay, we do have another question in the chat, but we're going to have to move on. So PV, maybe you could take a look at that and answer Diane in the chat when it's convenient for you. How's that sound?
Sure, that's
all right. Thank you. Thank you. We're going to move on. Our next case study is titled Carbon Removal with Corn Stover. Dr. Robert Brown is the Anson Marston Distinguished Professor in Engineering and Gary and Donna Hoover Chair in Mechanical Engineering at Iowa State University. He is the founding director and currently co-director of ISU's Bioeconomy Institute. He holds courtesy appointments in chemical and biological engineering, agricultural and biosystems engineering, and food science and nutrition. His research interests include advanced biofuels, plastics upcycling, and carbon negative energy. Dr. Brown has written over 300 scientific papers and book chapters. He wrote Bio-Renewable Resources, Engineering New Products from Agriculture, widely used as a textbook around the world. I will turn it over to you, sir.
Thank you, Deb. And can you see my full screen?
Yes.
Excellent. I got two screens and sometimes it gets a little confusing. So I'm going to talk about carbon removal with corn stover. And I'll just start by saying we pyrolyze corn stover to produce biochar and other products is our approach. So I want to give you some details and motivation for this. Pyrolysis is actually a very simple process. I'm showing a guy burning yard waste in his backyard, and he's producing biochar and he's producing bio oil as well. That white smoke, if you capture it, is actually a bio oil. We do this at temperatures of 350 to 600 degrees centigrade. We actually have three products. In addition to this bio char and the bio oil, there is a non-condensable gas that's is one of the products as well. And this is important to keep in mind in looking at the economics of this process and the amount of carbon, biogenic carbon, that you can actually remove from the atmosphere by this process. Let's just note for those that are not familiar with biochar, it is simply charcoal. And in this case, it's going to be a material that we're going to be sequestering in the soils as a way to do long-term sequestration. So instead of CO2 pumped underground into depleted reservoirs and such, we're going to simply spread it on fields where it will have long-term impact, including the fact that most of that carbon will actually remain in the soil over periods of time measured in hundreds, if not thousands of years. Whereas if we were to leave corn stover on the field, it would, over the course of a few years, essentially disappear. Now, the amount that remains depends on how the feedstock you're using and how you pyrolyze it. This example is showing something closer to 40% of the carbon remaining, but a lot of work has been done that shows it can be up to 75 to 80% of that biogenic carbon will remain in the ground. Many people that have heard about biochar have actually heard of it in terms of its ecosystem services. It can increase nutrient retention and improve water holding capacity in soils. It can even reduce nitric oxide emissions from soils. So lots of potential benefits of using biochar. I want to jump in directly to the kind of unique system of pyrolysis that we have developed at Iowa State University. We're going to focus on two important things. Instead of operating under a conventional pyrolysis regime, which means no air or oxygen is added, we operate with a small amount of air. We call this autothermal operation because it releases enough energy to actually drive the pyrolysis process. We don't need an external source of energy to do it. You can imagine that simplifies the reactor and has reductions in capital and operating costs. But we also recognize these three products I talked about. We need to capture all of those and make sure that it's part of the economic viability of the system. So we're going to focus on the bio, because I want to tell you, actually, the bio oil is more valuable than the biochar. So if you want to get the economics right, we can't ignore it. Another slide on autothermal pyrolysis. Again, it's a matter of putting a small amount of air into our pyrolysis reactor. I'm showing here at the bottom what we call the equivalence ratio, where if you have enough air for complete combustion, that's an equivalence ratio of 100 or 1.0. Pyrolysis is down on the left side of the screen, being 0%. 0% equivalence ratio. We're operating at about 6 to 12%. So it's close to traditional pyrolysis than it is combustion in this case. And by doing this autothermal pyrolysis, we have eliminated the heat transfer bottleneck that typically stands in the way for intensifying pyrolysis. My next slide is some experimental data that we've taken in our laboratories using the same pyrolysis reactor. In one case, we ran it conventionally. In the second case, we ran it under this autothermal operation with a small amount of oxygen added to the reactor. I'm presenting the data in terms of Sankey charts to get an idea of the process intensification. We were running it just shy of 8 kilograms per hour under conventional pyrolysis. And I'll tell you, we were a little surprised when we found that we could pump in almost 3 times as much biomass through that same reactor when we were not limited by heat transfer. In other words, we're using partial oxidation to provide the energy to drive the pyrolysis process. And you say, well, something's getting oxidized. There is a small loss on the heavy ends of the bio oil. It's almost immeasurable in this case. A small loss on biochar as well to drive this process. But the economics suggest this is the approach we should be taking. The other thing that I mentioned is we want to use all the products of pyrolysis. We think of it as a biorefinery. So it's not enough to take biomass, pyrolyze it, and produce biochar. We've got to look at what are we going to do with the other products. We've actually have a pretreatment we apply to biomass that we can produce sugars. This is not enzymatic hydrolysis. This is a thermal deconstruction of the cellulose and hemicellulose produced sugars. The lignin is converted into what we call a phenolic oil. There's an unrefined acetate from hemicellulose that we use for in-plant thermal energy, and of course the biochar. When we look at our first generation products, we look at the sugar being used for ethanol production. This phenolic oil is a bioasphalt, and that's not only a useful product, but it's a carbon sequestration product. I call it a carbon sequestration by the linear mile. And the biochar, of course, I've described it as a carbon sequestration product. We're also exploring in our laboratory potential future products that I won't get into today for time, but we do see some opportunities for even improving the economics. I want to show you here the kind of carbon removal that we can achieve. So think of it in terms of the kilograms of carbon that are removed, which would be a negative number, or is emitted in the atmosphere, which would be a positive number. And so when we look at all the inputs to our process, there are some that have positive emissions of carbon dioxide in the atmosphere, but there are also a couple of prominently here that have negative emissions, and that's because it is being removed from the atmosphere by photosynthesis, producing the biomass. And the green here is the phenolic oil being used as bioasphalt, and the orange is the biochar, BC. Both of these contribute negative, and if you look at the net emissions, we're actually getting negative net emissions of carbon dioxide in the atmosphere. In a sense, it's like these direct air capture where they talk about sucking CO2 out of the atmosphere, but we're letting photosynthesis pull it out of the atmosphere, and then we are going to convert part of that biogenic carbon into products that account for an overall negative. We're looking at corn stover, red oak, yellow pine in this example. We're comparing fast pyrolysis to autothermal pyrolysis, and you'll see in this case, all of these are negative emissions. Now, negative emissions is great, but not if it costs us a lot of money to do it. And that's some of my criticism of some approaches to carbon removal. All they do is remove carbon, and it's expensive to do it. So what we have done is analyze the cost of carbon removal. I want you to have your attention on the right-hand scale, the black scale. This is the cost per ton of CO2 removed as a result of this phenolic oil being a bioasphalt and the biochar as going into the soil. And we look at several scenarios of the cost. This red line is for, at the top is fast pyrolysis. You'll see it's a positive cost, as one might expect. It's going to cost money to remove carbon from the atmosphere, but it's only $25. And you've seen some scenarios that call for much more than that, $300, et cetera. But fascinating is when we switch from fast pyrolysis to the autothermal pyrolysis, here's a green line, where we haven't pre-treated the biomass, we actually go to a negative cost. But if we do a pre-treatment that's producing sugars, then when we have times of high historical sugar prices shown in this blue line, we can see dramatic drops in the cost of carbon removal that goes strongly negative. Just said, well, that's pretty fascinating. And again, it's because we have the bioasphalt and the sugar as products that basically subsidize the carbon removal. And I show this is under review. This paper was just published last month in Green Chemistry describing this if you're interested in more details. A colleague of mine said, why don't you go after the X prize in carbon removal? Those that are not familiar with that, this is an Elon Musk initiative, offers a milestone prize where you use some experimental data plus some projections of your ability to remove CO2, equivalent of 1 million tons of CO2 per year. There's 15 $1 million prizes of that. There's also a grand prize that's coming up, and that's to actually show 1,000 tons of CO2 removal. That's a $50 million prize. So we did enter that, and our concept is in partnership with Stein Seed Company, Frontline Bioenergy, and Iowa State University, using this ISU technology of using the biorefinery concept that I described with you, although we're not producing sugars at this point. And there was an announcement last year that we were one of 15 winners of the so-called milestone prize. It was based on this small scale pyrolysis equipment. I've got a map of the world showing where the prizes were, the bright purple colors. Iowa State University is located here. So you'll see we're one of these no coast awards. Most of the awards were along the coast or overseas. This is the Stein Pyrolyzer. Mentioned Stein Seed Company is doing the financing of this 50 ton per day system, the processing 50 tons per day of biomass. That's equivalent to removing 1,000 tons of CO2 in less than 100 days. So that would meet the requirement if we can get there. The system has been built as illustrated here. It's undergoing shakedown trials. See, we're producing biochar, but we're not running at steady state on this system yet. But this is our attempt to go after the grand prize of the X Prize program. And with that, I'd be happy to answer any questions. I think I've used up most of my time. But here's contact information for me.
Yeah, we have one question perhaps that can be answered fairly quickly from the chat. What is the corn stover half-life? Is it in a no-till field? And what is the mean soil temperature for the chart shown? It's in the chat if you need.
So in terms of the sequestration, we are doing trials right now using soil out of some of the Stein seed fields to determine the so-called recalcitrance of the carbon. Our initial analysis was based on some preliminary data that we had that suggested it was about 50%, 58% of the biogenic carbon was recalcitrant. But we are going to do these trials because the reason it reduces is due to microbial activity. And there's a fraction of the biochar referred to as labile that the microorganisms can consume. And that's usually consumed in the first year or two. So we're undergoing those trials to determine this recalcitrance. I don't know if that fully answers your question, but that's the best I can offer you right now.
Great. Well, thank you so much. I appreciate
My pleasure.
I'll appreciate the information. We're going to move on to our last case study. which is the Lanzatech Bioindustrial Carbon Management is the title of it. And we have Rachel Brenc, who is the Director of Commercial Development for Lanzatech, a gas fermentation company that utilizes a proprietary microbe to convert waste gases to ethanol and other fuels and chemicals in a continuous process. Whew, that's a big sentence. She was the lead process engineer on the design of a first of its kind commercial plant in China, which successfully started in 2018. She holds a bachelor's degree in chemical and biomolecular engineering from Cornell University and previously served as a reliability engineer for ExxonMobil. So Rachel, I'm going to turn it over to you.
Thanks, Deb. And thanks, Mary, for organizing as well. Looks like your dog really wants to get in on this Lanzatech talk, so let me know.
She is so excited about carbon management, she can hardly stand it.
I love it. I love it. All right, everyone. Thanks for having me. Happy to wrap up today and happy to kind of show a different side to carbon management through industrial biotechnology. We can utilize a lot of the residues from forestry, from agriculture as a feedstock, which I think is really powerful to helping continue that extending that carbon's life cycle. So we are Lanzatech here. We're innovating for what we call a carbon smart future, which is, I think I've heard someone say the kind of triple win, which is what we're focused on as well. And we believe that all the chemicals and goods that we use in our everyday lives can be derived from wastes that are already above the ground today, and not stuff that we have to compete with for value, not fossil-based materials, but things like waste gases, waste residues, even household garbage can all be used as feedstocks when you've got biology on your side. One thing is for sure in our carbon management journey is that we can replace fuels, most fuels, I'll say, with power, right? We are electrifying fleets faster and faster every year. Of course, there will always be things that need liquid fuels like aviation for the near term. But there's a huge market for chemicals that contain physical carbon that we can't do anything differently to make. They need a source of carbon. And so that's where we believe we can substitute waste carbon to make pretty much everything that you can buy in stores. And where's the source of this carbon? Well, we talked about agricultural residues already, plastic waste and garbage, but also industrial off-gases. If you think about the steel mills of the world, the refineries of the world, there are hundreds of thousands of tons of emissions out the stacks there every day. We've got a future where direct air capture is possible, where we can draw CO2 directly from the air, utilize that as a feedstock. And ultimately, where we choose to source our carbon will impact our climate future. Here's our first commercial plant located in Taofeiди in China, outside of Beijing. And at this plant, we're capturing the waste off gases from a steel mill and converting it to ethanol with our proprietary biocatalyst. Some folks call it a biocatalyst, some folks call it a bacteria or a microbe. The concept is the same. We're feeding gas to an organism that utilizes it as its sole source of carbon and energy. And that is how we can tap into that variety of feedstocks we've talked about on the previous slides. So it turns out microbes are really good at transforming carbon. They do a lot of things that no other human-made technology can do. We're talking about really complex cellular systems that operate across multiple scales. It's a catalyst that's self-replicating. So imagine not having to purchase and replace catalyst in your unit every year or two, but instead allowing the microbes to self-replicate and create their own new catalyst. We also understand now that we can modify these microbes to produce a whole range of other products beyond ethanol. Which is really exciting to use that same kind of chassis, that same host, to be able to produce a variety of products in the same facility. We're operating at low temperatures and pressures. So if you think about all the energy that's required to utilize wastes in traditional catalysis, here we can operate at much lower, the human body temperature, right? These kinds of things are safer and not as extreme for process design. So that's the core of our process ultimately, is this gas fermentation unit. And just like you can ferment sugars into gas, we're fermenting sugars into ethanol, we're fermenting gas into ethanol. And the microbes live 24/7 inside this bioreactor. It's a continuous process. So we're consistently bleeding microbes and ethanol product out of the system to be separated and recovered. And while we've commercialized in that first plant I showed you, steel mill off gas, we are scaling and are going commercial on our next generation of facilities that will utilize agricultural residues and municipal waste residues. We now have to bring in gasification, which is a process step that, as Dr. Brown showed in his slide, with kind of sliding up the scale of air requirement from pyrolysis, but it produces a carbon-rich off-gas that we can then feed directly into our system. And similarly, we can take advantage of that biochar as a co-product to the process. And then finally, in the not so distant future, we're already working on engineering for projects that use CO2 directly. We couple this with green hydrogen, as CO2 alone doesn't have the energy required to drive the reaction. So bringing in green hydrogen from electrolysis using renewable power can help provide what's needed to utilize the same platform to produce products. Today, we've produced fuel ethanol, and we've spun out a company to produce jet fuel from this ethanol to help solve that aviation decarbonization problem. But I think more importantly, we've also fixed ethanol into materials, and you'll see some examples of how we've utilized ethanol as a feedstock to make things like polyester, polyethylene, these kind of plastics and goods that I mentioned you could find in your supermarket aisle at the beginning of the presentation. And then finally, the heart of this kind of energies talk series is this circular nature. And so if we can, utilize the CO2 that is in the air from combusted fuels, feed that back into the process, or take end-of-life materials, when we're done with that polyester shirt that we made from waste, recycling that back through a municipal waste gasification facility. We've now truly closed the loop from fuel combustion and end-of-life material use, which is really exciting for the future. So we already talked about some of the advantages of biology, right? Lower temperature, lower pressure, but take a look at what we would consider a typical variability in a syngas we might get from, in this case, municipal solid waste. This would be extremely challenging with the fluctuating hydrogen and CO content. This would be extremely challenging to feed into a traditional catalytic system. But biology handles it like a champ. You can see on the right-hand side, here's the gas fermentation output from receiving this chaotic input. And you can see product selectivity holds relatively steady over time and quite stable, right? Doesn't impact the stability of the process. You can see that we can produce ethanol with very high selectivity and low byproduct selectivity, including the biomass of the protein itself that's produced during the process. So it's been a journey. It has taken us over 15 years to get to this point where we're commercially using industrial biotech to take waste gas to products. It starts back in the lab, which many of you are probably working on research projects right now. We started with a small reactor, proved that this could be done on bottled gases, but the real important part was getting into the field and utilizing these real life inputs to show that, yes, we can process not only steel mill gases, but others as well. This culminated in demonstrating the technology in 2012, 2013 with our first commercial startup in 2018. And in that time, since our commercial startup, we've mitigated over 200,000 tons of carbon dioxide emissions. We just plan to grow that exponentially as more and more plants get started up. And it's like any other chemical or refining process in that we can produce very stable long runs. This is an example of an over 100-day run. This is an improvement over traditional biotech, which may run in batch, which may run for shorter durations, and have that constant up and down. We'll be starting up our first European plant in Belgium. I would like to sign up for the startup team here. It sounds like a really great place to be. But here we're also taking steel mill off gas from one of Europe's biggest steel suppliers and converting that into ethanol. We're not stopping in just China and Europe. We've got a variety of feedstocks across the world we're looking to treat. You can take a look at some examples here. In India, the feedstock of choice is agricultural residues, so we have multiple plants in design there. We also are utilizing agricultural residues up in Canada with Suncor to prove out our next generation reactor. So a lot of great partners here, a wide variety of feedstocks to all accomplish the same decarbonization goal. So why ethanol? We know it can be used as a feedstock for many other things. We can produce ethylene in a one-step process, which I mentioned we can convert to jet fuel, but also a variety of chemical products as well, where it is truly stored in those products. And those include things like PET fibers. We did a launch of dresses with Zara. One of my favorite collaborations is EVA, which is the foam in your sneakers, with On Running and Borealis. As well as we can, create surfactants and purified ethanol for use in fragrances. And finally, beyond conversion of ethanol, we talked about that kind of endless potential of biology and what else we can do with it. And we know beyond ethanol, there are so many opportunities, including the ability to directly produce acetone, isopropyl alcohol, even monoethylene glycol, which are all important feedstocks for the chemical industry. We can utilize acetone to produce PMMA. We can use isopropanol to produce propylene and polypropylene. And we can use glycol to produce polyester and PET bottles. We have an entire modeling team dedicated to figuring out the next generation of microbes that we can then utilize the same hardware for, and in a way swap them out like software to produce the products that may be in demand. So in summary, we're programming microbes. Here's a nice shot of our synthetic biology labs, including our automation systems that help us engineer more microbes faster to produce new products like acetone and IPA that have a significant reduction in GHG savings. This allows us to rethink how we manage our carbon today, rethink what the traditional refining industry could look like. I think it's a great analogy to call the pyrolysis units a mini refinery. And that's what we're trying to do, is replace all these products by harnessing biology to make everything we need. And that will hopefully take us to the post-pollution future, where waste gases are no longer a pollution problem, but a feedstock for all. So that's what we had today. Happy to take any questions. Thank you.
Thanks, Rachel. Have any questions? We have about a minute. We can maybe take one question. You blew us away, Rachel. Got nothing to say.
I'll be around for the post discussion too. So.
Okay, great. I think maybe then we will, and we may be getting tired. It's been a long day, right? So sitting in front of our computers, so that could be part of the problem too. But we are going to ask you to generate a little energy here to engage in a focused conversation to wrap up the day. So just like we did before, Scott's going to put us into some focus, into some breakout rooms, and we're going to have a little focused conversation to reflect back on where we see gaps, opportunities, and where we might move in the future. So everyone hang on. Go ahead.
Deb, this is Tim Bay. Rachel, does Lanzatech have any plans for new facilities? The same scale as the current deployment?
Yeah, absolutely. And in the slides, you can see kind of a deployment map of where we plan on going. So to date, we have a few plants operational, and each year we plan on adding new capacity and new plants. So we have a consistent pipeline of plants that are in design, in construction and production. So
Do you have citing criteria that in high level, should there be facilities and possibly co-developer parties interested in opening up discussions?
Yeah, great question. And it depends on the feedstock. So when it comes to gaseous feedstocks, it's best for us to go to the waste, so we're not piping around dilute gases. So in that case, it's clear that we would site next to a steel mill or the refinery. In the case of solid wastes and things like agricultural residues, we would have to consider, a good radii to minimize that trucking and import. So again, going to the waste, but understanding there's some hub and spoke required to get the feedstock to site. So I think we would model it that way. And we're just like any other chemical processing plant, do have toxic gases, but it is otherwise a pretty innocuous process with pretty standard chemicals. So no other special considerations there.
Thank you.
Two quick questions in the chat. Have we checked on the health and environmental effects of these products? Not exactly sure which products she's referring to, but that's a question. And then is this blue ethanol?
Yeah, so the products are chemically identical, right? We are distilling ethanol in the same way that today's corn distillers do. So in that regard, there's not a fundamental difference between ethanol or IPA or acetone made via the fermentation process versus traditional petrochemical processes. As far as the blue designation, I've heard that applied to hydrogen as far as the source of the hydrogen and whether or not it's, still made from fossil, but the CO2 sequestered. In this case, we call it low carbon ethanol. Either way, there's a GHG emission savings tied to the ethanol that we calculate and, share with customers to get buy-in on, yes, this is a good thing to do.
And we have a raised hand. Lee, you want to go ahead?
Yeah. And municipal solid waste to demonstrate your process. That's a tall order. But do you have a package unit that you envision could go to every corn ethanol plant and just hook onto the carbon dioxide vent and say, this is a piece of cake, we're going to do this? Well, there's 130 plants in the United States, so you could put it on 100 of them probably.
Yes, absolutely. That's an excellent observation. It is a great synergistic pairing because, we're also making ethanol. So you have all the product management aspects right there in front of you to tag onto. And I guess with the recent US legislation on, the IRA with hydrogen benefits, we see great potential because utilizing that CO2 will require hydrogen, which can now be made, at a nice subsidized price. So we expect that to be booming over the next few years.
You have stock for sale?
We did announce our intent to go public last year and have made some recent press releases in regard to that. So have a look online at what's available.
Thank you.